Moving on, now I'm going to find the domain and range of g of x. Since g of x parent function, square root of x, which has a domain of x values between 0 and infinity, and a range of f of x values between 0 and infinity. I'm going to look at the shifts in this domain. So values affecting the domain would be x values. So here I have a shift 3 units to the left. So my domain will shift 3 units to the left. Similarly, I am adding 2 in the y direction, so my range will shift up 2 units. So it will now be 2 to infinity. So there's the domain and range for my function. Now, does g of x have an inverse? To answer this question, I'm going to look at my calculator. And I'm going to type in the function 2 plus the square root of x plus 3. Enter. And I'm going to graph this function and take a look at its graph. Once I have its graph, I'm going to transfer it over here. I'm going to apply the horizontal line test to check for inverses. What I do is basically imagine a horizontal line traveling through this graph, and if it touches the graph only at one position all along the line, that makes the graph 1 to 1, which means that it has an inverse function. If it intersected at more than one location, it would not have an inverse. But since it does, since g of x passes the horizontal line test, it has an inverse. Yay! So now let's find that inverse. Suppose this is g of x, which we already had. Find the inverse function of g of x. Give the domain and the range of its inverse. Well, since the domain and the range of g of x were between -3 and infinity, and 2 and infinity, the domain and the range of the inverse switch. So the domain of the inverse function will be between 2 and infinity, which was the range of my original function. And the range of the inverse will be equivalent to the domain of the original, -3 to infinity. Once I have that, I can go ahead and find the value of my inverse function. I'm going to do this informally. Since my original function here, I take the value x, I first add 3. So my first operation is adding 3. Then I take the square root. Then I add 2. To figure out what the inverse function does, I'm going to think of this in terms of my socks and my shoes. When I'm getting ready for work in the morning, I first put on my socks and then put on my shoes. To undo that, I have to first take off my shoes and then take off my socks. So what I'm doing is the inverse operations in reverse order. So to find the inverse, I'm going to start with what I did last and invert that. So instead of adding 2, I will subtract 2. Then I took square roots. The inverse of that would be to square it. And then I had added 3, so I'm going to do the inverse of that, which is subtract 3. So it's the inverse operations in reverse order. So f inverse of x should be equal to x minus 2 all squared and then subtracted 3. There's my inverse function of x. Now I want to verify that this is actually an inverse function. To do that, I have to look at the compositions of f composed with this inverse at x and the reverse composition. I do have to check both, and I'm checking that these values are equivalent to x. That's what I want to see. So let's evaluate it and see if they actually are. First, f composed with f inverse. This will be f of the value x minus 2 squared minus 3, which is equal to 2 plus the square root of x minus 2 squared minus 3 plus 3. My 3's here cancel out. So I'm resulting in 2 plus the square root of x minus 2 squared. Well, the squares and the square root cancels out, which is x plus x minus 2. And then my 2's cancel out, leaving me with x. So my first verification works. Moving on to the second. Give myself some room to erase this. F inverse of f of x would be f inverse of 2 plus the square root of x plus 3, which is equal to 2 plus the square root of x plus 3 minus 2, quantity squared, minus 3. Well, the 2's here cancel out. When they cancel out, I'm left with x plus 3 square rooted squared. Well, those will undo each other, and I'm left with x plus 3 minus 3, which reduces to x. So this verification also works. So since both of these compositions, f of f inverse equals x and f inverse of f equals x, I have verified that this is actually my inverse function. I should mention that I made a mistake. This was all supposed to be g, not f, so this should have been g composed with g inverse, and this should have been not f inverse, but g inverse. Sorry about that. Now I also want to verify graphically that the function I found in part B is the inverse of f of x. To do that, I can again go to my calculator. I already have my g of x graph, so now I'm going to put in my graph for my inverse function, which is x minus 2 squared minus 3. So I'm going to put that in. X, oh, I need parentheses. X minus 2 squared minus 3. Hit graph. You know, it may look like these are not inverses. Remember that inverses must be symmetric across the line y equals x. Just this line right here. It's not symmetric around that. They are not inverses. Now this one looks like it's a parabola. It has all of this part of the graph. The other one looks like only half of that. Well, remember there was a restriction in the domain for this inverse. Its domain is values of x only between 2 and infinity. So the parts of this graph, which I am considering, is between 2, starts here, and infinity. So that's my inverse graph. Here is my original graph. Looking at those, I can actually see that they are reflections of each other. So graphically, these are inverses.